Hello and welcome. Today we're going to take a look at Leetcode 230, kth smallest element in a binary search tree. Given the root of a binary search tree and an integer k, return the kth smallest value, one index, of all of the values of the nodes in the tree, of the values of the nodes in the tree. And here we have example 1 with this tree with 4 nodes, 1, 2, 3, and 4, and the smallest, we have k equals 1 and smallest element is 1. And then we have this other example, 1, 2, 3, 4, 5, 6, with k equals 3, so we return the third smallest element, node 3. The number of nodes in the tree is n, k is between 1, n, and 10 to the 4th, and the node value is between 0 and 10 to the 4th. And a follow-up, if the BST is modified often, we can do insert and delete operations, and you need to find the k smallest frequently. How would you optimize your solution? Okay, so how would you approach this problem? Well, let's see. Let's go to the drawing. Here we have the second example. It's a larger tree than the first one, so it's a better example. So how would we traverse this tree? We know we can traverse a tree in 3 different ways, right? We can do a pre-order traversal, a post-order traversal, or an in-order traversal. If we do a pre-order traversal, we see that our first node is already 5, so that doesn't really give us the smallest element. And if we do a post-order traversal, we'll have 5 at the end, so that also doesn't seem correct. But what if we do an in-order traversal? Well, let's see what happens. So we have here k equals 3 is what we need to find, and we can initialize a count also equals to 3. Okay, and then we check. We go down this tree on the left side, because that's how we do the in-order traversal. And then we go to node 3, and then we go to node 2, and then we go to node 1. And notice that 1 doesn't have any children, so there's no way we can go left. So now we process node 1 itself, and we ask ourselves, what is our current count? Well, it's 3. So we have to decrement our count to 2, because this is the smallest node, right? Decrement our count to 2. And then we go up to node number 2, and then again we decrement our count, because there's no right child as well, so count becomes 1. And now we're at node 3, and again, since we're processing another node, we decrement our count, and our count is now 0. And that means we can return our value. So we are at node 3, so we can just return the value of node 3. So notice that in the in-order traversal, we process node 1, 2, and 3. And if it continue, we'd go down the path of the right node, which is 4. So the in-order traversal gives you the sorted order of the elements in the binary search tree, only in the binary search tree. So that's why it's important that you have a binary search tree, and why the in-order traversal is the way to go here. So 1, 2, 3, 4, 5, 6 is the order in which the nodes would be traversed in the in-order traversal. Okay, so that's how we would traverse this tree and get our solution. But can we do it in another way? We can do it actually iteratively, don't have to do this recursively, if we use a stack. So we're going to initialize a stack here, STK, okay? And then we go down the elements again. So we push 5, which is the root node, we push it to the stack, okay? And then we go down the left side, we push node 3 onto the top of the stack. Push node 2 onto the top of the stack. We push node 1 onto the top of the stack. Okay, and now we have to pop 1 from the stack because we don't have any other elements to push on the left side. And for node 1, decrement k, and k becomes 2. So node 1 has no right children, so there's nothing else that happens with node 1. Then we pop node 2. Okay, so we are currently considering node 2, and we decrement k to 1. So it's only the second smallest, so we don't have our solution yet. We don't have a right child. So that's it for node 2. We stop processing node 2. And then we go to node 3 and pop node 3. And we decrement k to 0, which means we found the solution, right? So 3 is our solution, node 3. But notice that if we were to continue to process this, we'd go down the right child 4, and we'd push 4 to the stack, right? And then we'd pop it from the stack, it has no children, and then we'd pop 5 from the stack and push node 6. So that's how we would traverse the whole tree using the stack. I hope that's clear, and let's go to the code to see how these solutions would look like. Okay, so here we are in Leetcode. So first we're going to use recursion to solve this problem like we did initially. So we're going to define a helper function. And if we don't have a node, we return. And we also initialize a count variable and a result. And actually the count is going to be initialized to k in the beginning. And then we call our helper function with k, and we return our result, which is initialized with -1 in case we don't find anything. And we go down the dev path. And then at some point we need to go down the right path. And before we do that, we decrement our count. And we check if our count is 0. If our count is 0, then our result is the node value, right? And otherwise, we are at -1, so the 3 test cases pass. And our solution has been accepted. Okay. So that's one way to solve this problem recursively, and then we can also solve it iteratively. And now let's take a look at implementing the iterative version using a stack. I'm going to create a new function for this in orderIterative, and I'm going to pass in node and k. Then we just return this. Root k. All right. Then we create our stack. STK. And while our stack is not empty, or we have a valid node, we go left on the left subtree, and we keep going left while pushing the nodes to the stack. All right. Then, since we are in an in-order traversal, we process the current node. So we take it off from the top of the stack. and then we go right if we have a valid node. All right, so what we still have to do is we have to check if k becomes 0, we decrement k, and if k becomes 0, then we return the current node value. And if we don't find any node, we return -1. All right. Okay, so it passes those 3 cases, and it passes all cases. Okay, so what's the time complexity and the space complexity for this? So the time complexity is going to be O of h plus k. In the average case, where age is the height of the tree, and that's because we go on the left subtree, so we iterate basically the height of the tree before we start popping those k elements of the stack. So that's why it's h plus k, but actually this resolves to O(n) plus k in the worst case, because if the tree is skewed on the left side, then we're going to go all n nodes. We're going to traverse all n nodes on that side. And we also know that k is at maximum n, so this resolves to O of 2n, which is O of n. And the space complexity is O of h, average case, and again O of n worst case, because we can have a skewed tree if we have a left skewed tree, for example, and then we have space complexity also of O(n). So let's see what it says here. Time complexity O(n), space complexity O(n). All right, so that's it for this problem. We also had a follow-up question. It can be, so the question was, if the BST is modified often, we can do insert and delete operations, and you need to find the case smallest frequently. How would you optimize? And the way you can do this is with using a linked list, data structure doubly linked list in the tree node. And then when you compute the case smallest, you can get the optimized O of k runtime with the optimization of using a doubly linked list in the tree node. And you also have to use that for insert and delete. So the insert and delete operations are going to be a lot more complex, but the case smallest is going to be running OK time. So that's going to be faster than what we have now. Okay, but we won't modify the tree node right now. I think just giving such an answer will suffice for the follow-up question. If not, you can go ahead and try to implement it using a doubly linked list. So thank you for watching. Like and subscribe if you enjoyed it, and stay tuned for more C++ problems. Thank you and bye.